Hello, colleagues. I'm Sergey Shumsky, head of Cognitive Architectures Laboratory, and today I'm going to talk about our path towards AGI. First, I will dwell on the differences between AGI and narrow AGI, and my answer is in being creative. Then I'll explain how to provide for creativity, and then I'll dwell on the architecture of AGI, or strong artificial intelligence, that we're developing in our lab. So, what is the main trait, species trait, that makes a strong AI different from narrow AI? There are lots of definitions of AI, of intelligence, basically, more than 100. And we'll be surprised to see that this trait is creativity. That's the ability of creating something new, going out of the box, beyond the known. Let me give you a couple of examples. Intelligence is defined as an ability to solve new, out-of-the-box tasks, or to achieve goals in unfamiliar situations. In other contexts, universality, autonomousness, and the ability to learn. But if you think about it, they all depend on creativity. But let's proceed from the criteria rather than definition. For instance, there's a Wozniak test. So the robot is considered to be intelligent if it's able to brew coffee in an unknown kitchen. Yes, indeed. In this case, the robot won't be able to follow a guide, an instruction. It will have to automatically decide, like where to find the coffee maker or what to use it to replace it. If we take a closer look at the situation, we can identify the main components of creative intelligence. Firstly, active hypothesis generation. So in order to build ideas of how to achieve your goals, in order to achieve these goals, you need to decompose complicated tasks into simpler ones. And finally, you need the capacity to foresee and assess the outcomes of your actions, to optimize your plans and ideas. Modern neural nets don't yet have a full set of such traits, but they can do something, and they can do something very well. In particular, they can recognize images quite well, that's decode information, or to solve the inverse problem, generate images, enriching abstract information with a lot of specific details. I can say that in this capacity, neural nets have imagination. On the right, in this slide, we see a picture of a person that doesn't exist. It's a neural net generated it in the website. We can teach coders and encoders jointly, just like is done in variational autoencoders. And by the difference between the initial and the final picture, to do a gradient learning. So this is the strongest trait of modern AI. But as a weakness, we can say that gradient learning is very costly. So the cost of learning grows with the square of the learning points. So if you have 1 billion weights, then this net will run for a second in a normal processor, but for its learning, it will require 1 billion seconds. That's about 30 years. So the learning of this net will require supercomputers, which is not too good if you think about robots. But even being able to access supercomputing capacity won't guarantee that you'll be able to plan behavior in an unknown situation. Of course, had we known how to behave in all sorts of situations, we would be able to teach the autoencoder. But you all understand it's not possible, even though some robots learn exactly this way. It's enough to show them what they need to do and how. And after that, you can put them at the production line or where it's relevant and it's good. But we understand that these robots will never be able to make us a cup of coffee in the kitchen they don't know. For this, they lack the ability to achieve their goals on their own without a teacher. How can you plan behavior when you don't have samples? We just can't enumerate all the possible plans because the number grows exponentially. Nevertheless, the human brain somehow copes with its tasks. So sitting for all our lives in our heads and talking to the world only through the neural impulses of its sensors and actuators, and sometimes getting some moral support. But nevertheless, it appears to be able to generate quite sophisticated behavior in people and the ability to foresee the future for years ahead. So the creativity lies exactly in the plane of the ability to generate long and sophisticated plans without samples. Of course, we can generate long-term plans step by step, just like AlphaZero does it. The deep AlphaZero neural net has deep intuition. It's able to foresee good moves in any situations. But for the longer term, they use the brute force to enumerate. Of course, the presence of intuition brings down the number of variants of options, so makes this combinatorial explosion kind of directed, but it doesn't. It remains being an explosion, and the number of options grows exponentially. So AlphaZero cannot, foresee beyond several dozen moves forward. But people, as we know, think in a very different way. We always have a rough idea if we want to achieve a long-term goal. We decompose it into stages and address them as they arrive. And this way of reasoning and planning is much more economical compared to brute force enumeration of all the possible options. But unfortunately, we don't know the algorithms for such a hierarchical deep learning. Let me refer to Stuart Russell, the author of the well-known textbook on artificial intelligence. In his latest book, he's writing, currently, all the existing methods of hierarchical planning rely on human-generated hierarchies of abstract and specific actions. We don't yet understand how these hierarchies can be derived through learning. Following Russell, I believe this is the central problem on the way to AGI, and it's exactly this that we are trying to address in our lab. We are developing a system of hierarchical planning where each computing layer solves a relatively simple task, generating plans several moves ahead. But it does each at their own time scale. So the lower layers will be specifying plans for the higher one. You can say we have a stack of encoders that work in the combined schematic, and in such schematic, creativity is kind of spread across the entire computational system. And instead of just one combinatorial explosion, we get a lot of small combinatorial explosions with controlled complexity. As a sample, we've taken the only strong intelligence system that we know of, the human brain, and we know the role of interaction between the cortex and the more ancient structure, basal ganglia. We know how it happens. There are feedback loops such that basal ganglia can impede any area of the cortex if its activity is not following the purposes of the system in terms of the ganglia. It's there that all our values reside, and it's there that they form with reinforcement learning, where the reinforcement is done through additional signals from even more ancient parts of the brain, from the stem. If we digress from all these biological details and just looks at the schematics of the process, we'll see a clear hierarchical picture consisting of a lot of similar modules. And that's why if we understand how one of such modules operates, then we'll be able to reconstruct the operation of the entire system. This has been done, and this gave rise to the deep control architecture that consists of identical hierarchically organized modules, and it runs like this. At the input, the system gets a sensomotoric vector. So the status of all the sensors and actuators at a given time. And at the input, the system predicts the state of this vector in the next moment of time. If the prediction realizes, then the system reinforces itself and gradually gains the ability to predict the outcomes of its actions at all the stages. And the transition from stage to stage is done through the merger of actions in psychological patterns, just like you can use single letters to form words and to use words to form sentences. So each next level works with larger entities than the previous one. So if we take a look deeper inside a typical module, we'll see several subsystems there with clearly identifiable functionality. For instance, the coder does discrete coding of the vector input. The parser identifies typical patterns in the incoming flow of signals and remembers correlations between them. And the presence of correlations in the semantic memory allows the planner to foresee all the possible options and choose those that promise the biggest reinforcement. And finally, the decoder decodes the predicted plans to the lower level, and the lower level gets the situation by the current context in the form of a context vector that has a row and a column from the semantic memory. This way, what we're getting in the system is all components of the creative intelligence that I started this presentation with: the ability to generate hypotheses, to decompose a task, and to assess the outcomes of your actions. In order for this concept not to be just paperware, we're writing program code. We call it ADAM, Adaptive Deep Autonomous Machine. So this slide shows the ADAM pseudocode, which turns out to be quite compact. And this slide shows the results of experiments with ADAM. These are the first experiments with the simplest single module ADAM on a very simple task-mounted car. We need to run this car on the mountain, considering that there's not enough power in the engine. So the idea here is to come up to the idea that you need to swing the cart, and ADAM has coped with this task. So, of course, we understand that we're at the very start of the path to the strong AI, to AGI, but we have a clearly defined research program relying on Feynman's principle: what I can't create, I do not understand. We are planning to create acting models, test them on the existing tasks, and our final task is quite pragmatic: to create a single modular architecture for a robot brain, based on which you can create different robot families that can learn to solve different problems that are valuable to people under their guidance. Thank you for your attention. I'm here to take your questions. Sergey, thank you. Well, perhaps there'll only be one question. What, in your opinion, is the main hurdle on the way to AGI? The lack of computing power, the lack of required architectures, neural networks, or else? The lack of required architectures. Because a good architecture will solve the capacity problem. You need to go away from the square law, square dependency on the complexity. Okay, we don't yet have any questions from the audience. Look, I know your architecture a bit from your earlier workshops. As far as I can see, even though you're saying that you use the principles of human brain when designing this architecture, it's still quite homogeneous. You know that human brain is quite modular. There are different sections responsible for different functions. For instance, where do you have memory? How do you plan to do persistent memory, volatile memory, or it's not a problem for your architects? Well, we have two types of memory, semantic memory and episodic memory. But so far, we're fine with that. Semantic memory is located in the cortex, and episodic memory is usually attributed to hippocampus. Well, the simplicity of our architecture is in that we've indeed tried to single out a module that contains all parts of the brain, both the cortex and ganglia, and the negro substance and hippocampus that work together in such a modular architecture. Thank you. Another small question. You are continuing your developments. Can you describe where you are now, what you can already showcase, and what specific challenges are you facing? Well, we're just developing, trying to solve all the problems that emerge on the way. There are lots of them, of course, because the devil is in the details, and we're trying to deal with this devil, with these details. So there are no problems of principle that I can see. Is there anything to showcase, a demo version? For instance, you mentioned the cart that runs along the paths. Yes, we have a bench on the MIPT website where you can play with this card. Okay. And we'll be developing it, adding new problems from the AIG collection. Sergey, thank you very much.